Let's talk about an important aspect in our script. I programmed algorithms for solving systems of linear equations and also for doing integration. Whereas the functions for the linear systems are perfect, the integration functions are not perfect. I kept the code simple to be better understandable, but we have a problem, for example, with Quad-Simpson. We don't have a problem with Quad-Simpson value. This is brilliant, this is perfect, but Quad-Simpson is a problem. I want to show you the code again. This is the Quad-Simpson value code, and this is perfect. So you can use that code. Perfect. Okay, but you should not use this function. And the problem is that we start here with n is 1, and so we evaluate the function at the starting point of the integration interval and at the end point of the integration interval, and then also one point in between. And then doing so we get an integral value, the value of the interpolating polynomial of degree 2, and that is our value I1. And then we split the interval, what means that we also evaluate at these points, and then we are using the formula 1 times that function value, 4 times that function value, 2 times that function value, 4 times that function value, and 1 times that function value. And then we get an integral value I2, and then we check the difference I1 minus I2, difference absolute value. And if this difference is small, then we return, we stop doing anything, and we will return our integral value, and the function will terminate. So what is the problem? And all the other algorithms, trapezoidal, Newton-Cotes, Gauss quadrature, they all do the same. First find a very crude integral value and then refine 1 times, and if the difference is small, then stop. If it's not small, refine once more, compare the difference. If it's small, less than a tolerance, then stop, and so on. And this is a problem, as we can see here in this situation. What is that function? 1 minus cosine 240 times pi times x. This function looks like the following. Here is 0, here is 1, and here is 2. And this function starts with the value 0, and then 1 of that, and then we have 1 period later again a 0, and then again. We have zeros here, and so on, and in the end we are here, and that is position 1, this was position 0. And how many oscillations do we have? In this case we have 120 oscillations. So this is the point 1 divided by 120. This is the point 2 divided by 120. This is the point 3 divided by 120. This is 4 divided by 120. And this is 119 divided by 120. And then here we have the 1. Okay, this is the situation. So what will happen if we do Simpson value? Then we will evaluate the function at the starting point, at the end point, and at 2 points in between, and these 2 points will also be points of this kind. And so we will get integral value 0. Our I1 is 0. And then we refine, then we split the interval, and what will happen? We will have a 0 at every position we will evaluate, and thus we will also get I2 is 0. Then if we check the difference, we see there is no difference. The difference is less than the tolerance, difference is 0, and so we will return integral value 0. But that's not true. Our function is positive most of the time and is never negative. So the true integral value is not 0, but in that case it's 1, I think. And so this is a catastrophic result. And we will also get zeros if we apply all the other formulas. And you can see that by typing in that code, and then you see a 0 for trapezoidal, you see a 0 for Simpson, and you see 6 times a 0 for the Newton-Cotes, which is no surprise, at least for k is 1 and 2, because this is trapezoidal, 1 is trapezoidal and 2 is Simpson, and we see a 0 all the times, and this is nonsense. The true result is indeed a 1. But if you are a professional programmer, and then what can we do? What can we do if I think a very long time about? If you are a professor, then in the summer, then you have 2 months and you can think about whatever you want, and then maybe you spend a long time or you think a long time about that problem. And what is the remedy? And to be honest, I don't know an elegant remedy. And so you can say, okay, what is MATLAB or what is Octave doing? Maybe I can find out what this professional code does. And I show you the result. If you do the following, in MATLAB and in Octave, you have the quad command. And what you can do is write type quad. And then the code you will see on the screen. Unfortunately, I'm using Octave, and in Octave you can't see the code of quad, but in MATLAB you can see. And then also this one, here you can see where is the code, in which folder is that code, and then you can copy that code to your folder, rename a little, and then with the MATLAB editor you can go into the code, you can remove some semicolons, you can insert some pause commands, and then you can study the function and you can try to understand. The true story is that there are hundreds of lines only dealing maybe with wrong inputs of the user. So most of the code is check the input and give a warning or give an error. But if you're patient, you will find the lines in which the logic is implemented, in which the true algorithm is implemented, and then you can study what happens. And that I did. If you want to, ask me, and then in MATLAB I can show you the lines, the interesting lines, where I found out the following. MATLAB, the idea of the makers of MATLAB is a very, very simple idea. If you do integration on the interval 0, 1, then MATLAB tries to avoid the situation above. Okay, and what is the idea? He splits the integration interval into 3 parts, and this number is some number, I don't know. Is that the 1 second idea of the programmer, or is there a deep logic? This is maybe a very special number, 0.27158. I don't know if this is a very special number. Please, if you know, please let me know. Tell me what is that number. MATLAB splits the integration interval in the first 27.158% of the integration interval, and there he applies more or less the logic we implemented. So get an integral value, refine 1 times, and if the values are close together, then assume that this value is the correct one. Then integrate on that middle part, and then it's perfectly symmetric, the length here and the length here, and then integrate on that part. And that's all. That's the special idea. And then if you have a function of that, you split the interval. In the beginning it's that, but where the split is, you are maybe this. And then the first integral value which looks like more or less like that. Evaluate at these 4 points and then integrate the interpolating polynomial and then split in 2 parts here, and then you get some other values and you never get these 0 values. So this is the very, very simple idea of MATLAB, and this idea is used to avoid the situation we had above. It's no guarantee. Maybe by coincidence you have the unfortunate situation, then also MATLAB can produce nonsense results. That's true, but that's life. It's not possible to get really perfect code, and I am really astonished that this simple idea is the remedy in the professional software MATLAB. If we talk about studying what is internally going on, then I tell you, use type quad, use which quad, and use help quad. And these 3 commands will help you to better understand the MATLAB code if you want to. And doing integration, there's a quad command, and the second command you can use is integral. This is an alternative for quad. These are the 2 commands I am using when doing integration in MATLAB. I'm using either quad or I'm using integral. Okay, so we are done.